Good morning, students. Today we would begin the topic of heuristic search in AI. No, exhaustive, actual search techniques. We will look at search techniques. Students, please make it interactive class. I'll ask you some questions. Please respond. Now, suppose let us play a game kind of thing. Okay. Suppose do you know that there is a game? What is that called as? Where we have to search for the items. Anyone know the name of that game? I think hidden treasure. Hidden treasure or hidden objects. That in that game, what happens? Your friends and your siblings will buy something for you on your birthday. Okay, so you are here. This is you, and you have mm, friends and sibling. All right. So now imagine that uh, they have purchased a gift for you on your birthday. It's your birthday, and uh, you people have gone to a big resort. In that, the arrangement is like this. There is a room. In that, there is another room. In that, there is another room. And also there is a room separate from this. Is not connected to this. In that, there is one more room. And there are few rooms here at this side. Within this room, again, there are some rooms. Consider that it is a very large resort where there are so many rooms. And now, suppose your friends have kept your birthday gift here. And there is one birthday gift here. All right. Now, They wish you and they tell you to go and search. How will you search? Anyone, please tell me. Students, please participate.
Search room one by one, ma'am. That's it.
Pawan, very good. You will search one by no. You tell me how you will search. Suppose I have given the names A, B, C, D, E, F, G, H, I, J. Suppose here also there is a gift. You tell me in which order will you search? How from where? Okay. Hmm?
Starting from A, ma'am.
You start from A. All right. You start from A. Then
Ma'am,
from A
I'll
where?
start from whichever is near to me, I'll go with that.
Okay. Uh, very good, Manasa. So here Manasa is saying near to her. Okay. And Pavan is saying start with A. Any other answer? Pavan, from A where will you go? Will you enter B or you come out and enter D or will you go to F?
Ma'am, I will follow a sequence, ma'am. After A, I will search in the entire block of rooms.
So you go to
B
B.
and then C. Hmm.
You go to B.
If
Then from B you go to C.
hmm.
There you find the gift. You take it because you have more two gifts. So what you have to do?
Again coming back from the block and then searching in other rooms.
Hmm. You come out of that block and then you search. You may enter D. Okay, this is very nice. Anyone, any other student? Do you have any idea how to search? This game is played by friends. Uh, this is known as hidden treasure. Even in parks, gardens, wherever we go, we hide the things and we tell them to go and search. So here the problem is we'll write what is the problem and what is the solution. The problem is, let me write with this. Problem is to search for gifts. Solutions have been given here by some of two students. Any other solution, any other student, please come up with some other solution. No one? All right, let me proceed. The AI system has been given the problem. What is the problem? The problem that has been given to AI system is to perform search. Actually, to solve a problem through searching. This is one of the methods or strategies through which AI could solve a problem. The problem is what we and the analogy that we studied is we want to solve the problem of getting the gift by searching, and we move here and there and we try to search. The same thing applies to artificial intelligence, where it tries to find uh, the problem or the solution to the problem by searching. There are primarily two kinds of searches in AI. The first search is known as exhaustive search. It is also called as brute force, uninformed, unguided, or blind search. The synonyms to exhaustive search is blind search, brute force search, uninformed search, unguided search. These are the names given to exhaustive search. In this kind of searching, there is no information available to system for solving the problem. It does not know any, uh, it does not have any idea about the problem domain or the task at hand. It does not get any hints. That is exhaustive search. Exhaustive means it has to explore all the options that are available. This is exploring all options. The second kind of strategy is known as heuristic search. Heuristic search is also known as informed search or guided search. Here, some kind of information about the problem is given. About the problem domain is given. Again, coming back to our analogy, the example, what happens when you know, suppose if you know that your sibling is very lazy, okay, this is one attribute which you know about your sibling, lazy. If your sibling is lazy, then this is like a kind of some information about the domain. And how do you exploit this information? If sibling is lazy, whichever is near to sibling, whichever place is near to sibling, eh, that the sibling will hide the gift there. Okay, this is the information which you get from this property because you know about him or her. And suppose you know that out of these three friends, one friend is um, one friend likes to explore, likes to visit all the places that are at hand, that are available. So what he will do? He will go and check all the places, all the blocks, all the rooms, and all halls, and then he finds a place which is very much hidden. So you know about this friend. He is very adventurous. Okay, when because he's adventurous, he obviously hide somewhere here or here. And there is one more friend, you know something about him, and this also you know something about him. Means, what does it mean? It means that you have got uh, information about the domain. When you got the information about the domain, it is known as informed or guided or heuristic search. In the first case, where we tried to find the gift without any information, we just started with the A block, or we started with the block that is very close to us. Some, you arbitrary, you are using arbitrary methods you have started. But in the second strategy, what you do, you think, you analyze, you know about the people, and then based on their nature and attitude, you try to uh, find and search for the object. The method in which you have no information at all. Suppose when you come to college for the first time, you don't know what type of teachers you have and what is the nature of each teacher, what is the approach, how they treat you, and everything related to these academics and all. You have no idea at all. That is known as exhaustive search. Then what you do, you try to find the information. Once information is gained, it becomes a heuristic search. These are the two categories. Let us begin with the heuristic search. The first kind of technique is heuristic search. Oh, sorry, exhaustive search. There are four searching strategies in exhaustive search. The first one is known as breadth first search. Second one is known as depth first search. Third one is known as depth first iterative deepening. Depth first iterative deepening. And the last one is bi-directional search. You can also note down all these points in your notebook. But these are the four kinds of exhaustive search strategies. We'll begin with the best first search. First, first type of exhaustive search is breadth first search or BFS. Okay, BFS is a breadth first search. In breadth first search, let us try to understand this with an analogy. Um, okay, we'll go with that hidden treasure. In breadth first search, you start with the first room, okay, or the first hall, okay, first hall of these four halls. There are four halls. How you begin is you begin with you go to A and then there is nothing. Then what do? You come out of it and go in breadth wise. This is known as breadth. The horizontal, you know, along the horizontal, whatever is placed, that is known as breadth, and vertically, whatever is placed, that is known as depth first. Depth means you go vertically, inside and inside and inside. And if you go in a breadth first manner, um, you come out of it. If it is not available, come out of it, go to another one. Here also it is not available, go to next one, take it because here it is available, come out of it and start searching for another one in the same manner. This is breadth first search. It expands all the states one step away from the start state. All right. And then further, it expands all the states two steps from the start state. Later, three steps from the start state until the goal state is reached. is Bfs. Green color is Bfs. To represent this, we use a graph, a directed graph that has vertices and edges. Vertices, connect with the edges, connect with another vertices through edges. So it will be like this. There is a start node or start vertex. Start as the successors. These are called as successors or the childs. C1, C2, C3. Three children. Okay, this is a directed graph from start. You can go to these three. You can generate three successors. After that, suppose C1 has more two successors. So C11, C12. C2 has only one successor, C21. C3 has four successors. So C31, C32, C33, C34. All right. And in this manner, this graph grows. Generation of these successor nodes happen. Eventually, there will be a goal node. Suppose goal node is here, C311. This is our goal node. Here also there are some expansions. But our goal is this. This is the goal node. Okay, this is goal node. This is the start node. All these are intermediate nodes. In BFS, the search proceeds in a breadth manner, breadth-wise. It is a breadth-wise search. So to perform breadth-wise search, the search proceeds in this manner. S to C1, this is first, then to C2, second, to C3, third. Then it goes to next level. This is at level, consider this is at level 1, this is at level 2. Level 2 is just one step away from start that have been expanded. All the vertices that are one step away from start have been expanded. Next, level 3 will get expanded. After 3, this is 4, this is 5, 6, 7, 8, 9, 10. All right, level 3 is completed. It goes further to expand level 4. Level 4, this is 10, 11, 12, 13, 14, 15, 16, 17, 18. At 18th expansion, it finds the goal node. This we can relate to our water jug problem. In the water jug problem, we have start node as 0, 0. What does this 0, 0 denote? Will anyone tell me? What does this 0, 0 denote? What is a water jug problem?
Filling a 5 liter of jug with 4 liters of 4 gallons of water.
No, from starting you tell. That is the goal. What you said is the goal. What is the start?
Okay. Both are empty now.
What are both?
5 gallons.
Very good, Vani. What these are water with empty jugs. It's like it's not water, it's empty jugs. There are two empty jugs. All right, that is denoted by 0, 0. And the capacity of these jugs are 5 and 3. Okay, yeah, we can call them as A, B. This is our start state. From start state in breadth first search, how do you proceed? You go to what are the options? The options are the first
1
one
0
is
or 0 1.
50, second one is 03,
03.
50 and 03. These are the two options. So first you fill uh, this 5 liter jug. This is one way. Another way is fill 3 liter jug. So there are two successes that have been generated. From 50, what are the options? The options could be emptying this 5, so it becomes 00, or it could be filling this 3 liter jug as well, so it will be 53, or it could be uh, transferring water from uh, 5 gallon to 3 gallon, so it will be 2 comma 3. These are the three options. So these three successes would be generated at the next level. You understand, students? Then here, what are the options? Will anyone tell me what are the successes that could be generated at this side?
53,
Yes, 53,
30, 30,
30, right,
00.
right, 0. These are the options. We know that we cannot expand this further because it is like going to start state. All right, this is like a looping kind of thing. This will be stopped. From here, we don't generate successes. And here also, we don't generate any successor. Then what is left? Here we are left with these nodes. 5, 3, how from 5, 3, where we can go?
Either 5 comma 0 or 0 comma 3, ma'am. So it will start looping again.
Hmm. So then 2 comma 3, this is looping, so we will not take it ahead. This will stop. 2 comma 3,
2 comma 0, ma'am.
2
Or
comma
0 comma 3.
2, oh, 2 comma 0, 2 comma 0, and 0 comma 3. 0 comma 3 means again here, this side. Um, so we should not expand that. We should stop that looping. From here also, 0 comma 3 and this we don't explore. Here we explored. Now we should consider this 5 comma 3. 5 comma 3 already we have here, so we will not explore this. 3 comma 0, from 3 comma 0, what are the options we get?
3, 3,
3 comma 3,
0, 3.
this is 3 comma 3 means 5. How 3 comma 3? This will be, you are transferring from 5 gallon to 3 gallon. So it will be 0 comma 3. It will be 0 comma 3, or you throw away the water, it would be 0 comma 0. Students, did you understand this? 3 comma
Yes, ma'am.
0 means there are two options. Either you can transfer, so it would be 0 comma 3, or you can empty it. So it would be 0 comma 0. Both options we should not explore because we have it here. 0 comma 3, it would lead to loop. 0 comma 0, here it would lead to loop. This we would stop. Then which one we expand? This 3 comma 0. There are some other options as well. What are the other options? 0 comma 3 we don't expand. 0 comma 0 we don't expand. Then there is one more option here. Yeah. Someone said that it is right, but you have not given the reason. Whatever you said is right. Okay, 3 comma 3 is also possible because tap is there, no? From tap we can fill this. 3 comma 3 is also possible, and what is possible? 5 comma 0 is also possible. Why 5 comma 0? Means already 3 gallons of water is available in 5 gallons jug. If you fill it up, if you fill it up totally, then it would become 5 comma 0. So that option is also there. Out of these two options we will not explore. This 3 comma 3 and 5 comma 0 also 5 comma 0 we will not explore because 5 comma 0 is already available. 3 comma 3 is there. From 3 comma 3, what are the options? No, we have to come to this side. This level 1 is completed, level 2 is completed, level 3 is completed. Students, will you complete this graph and tell me, or we can call it search tree? Will
Yes.
you complete and tell me? I'll give you 2 minutes of time. Okay, and has anyone done it? Has anyone reached the goal?
Yes, ma'am.
From where?
From left side subtree, ma'am.
Yeah, very good. Tell me.
Uh, After the 2 comma 0, there will be 0 comma 2.
Right.
So if at all we fill that again, then with any other option, then it will start again looping
Hmm.
like 2 comma 3 or
Hmm.
0 comma 0 or 0 comma 3.
Hmm.
So from there, 5 comma 2 now,
Right. Very good.
and one more possibility 5 comma 2, but I think 5 comma 2 or 5 comma 3 that will start looping again.
Hmm.
So from 5 comma 2 we will go with the 4 comma 3.
Yes. Very good.
Now 4 comma 0.
Yeah, we can make it 4
Yes, yeah,
comma
we reach
0.
the goal.
Actually, it doesn't matter. It can be 4 comma 3 or 4 comma 0. What matters in the problem is 5 gallon should have 4 gallon water, and this should be 4 comma y. This y could be 3 or 0. It doesn't matter. So we have reached the goal state. We have reached the goal state. How did we reach the goal state? By expanding breadth-wise, level-wise. All right. This is known as breadth-first search. How this breadth-first search is implemented? To implement this in the form of algorithm, it maintains two lists: open list and closed list. What it does is it starts with S, means starting state. S, and then it uh, it compares whether S is a goal node. If S is not a goal node, what it does is it moves S from open to close, and it brings uh, the successors of S. Suppose we will name this as this is A, this is B, this is C. So it brings, or otherwise here we have no S, C1, C2, C3, C1, comma C2, comma C3. These three it brings in the open list. Now the question that arises is which one it should consider first for expanding. Will anyone tell me here? Because there was only first S node, it took S node, it removed from open list, placed in the closed list, and bring all its successors in the open list. Now the question that arises is here whether to take C1, C2 or C3 and compare it whether it is a goal node or not. If it is not, place it into closed list, bring its uh, successors. Students, please think and tell me this, no? Someone, which one to consider? Did you understand my question?
Once again, ma'am.
Okay. Here, this is the implementation part. To implement the graph search algorithms, uh, we require two lists, one open list, one closed list. And there are states, start state, goal state, and intermediate state, successor states. All right, start state, goal state, successor states. These are states. And then we have open and closed list. These are the data structures that we require in order to implement this algorithm. My question is, you start with start state S. You place it in open list. Open list is a list where all the nodes that have not been explored will be placed. When when we have to explore it further, we need to pick a node from the open list and bring its successors in the open list, remove the parent node from open list and place it in the closed list. That is what is happening here. It takes S first and place in the open list. Where is S goal node? It is not a goal node. Because it is not a goal node, what it does is it brings its successors C1, C2, C3 in the open list, means it expands C1, C2, S. It expands S and it removes from open and place it into closed because now S has been expanded. Means X has been explored, which means S is no more to be considered. All right. C1, C2, C3 have come in the open list. My question is, which one I should choose? Whether I should choose C1, or C2 or C3?
Nearest to the root
How do you find nearest to the root?
path.
Okay. Do you remember stack and cube? What is a stack and what is a cube? These are the two data structures.
In stack, both insertion and deletion done at the top of the list.
Yes. So
And
which policy it follows? Tell me the policy.
First
Last
in,
in, first out.
Last in, first out is the policy of stack. What is the policy of queue?
First in, first out.
first in, first out.
First in, first out.
First in, first
First
out.
out.
Um, Students, you might have studied stack a queue, but this is the application of it. Here we are trying to use uh, to implement BFS. We have to use queue. Here, open list is a queue. Here we implement open list as queue, and we implement close list as stack. But don't bother about closed. Just remember open list. Open list is a queue. Queue means first in, first out. So C1 is first to be in. So C1 will be first to be out. C2 is next. It comes out next. And the last is C3. So C3 would be considered at the last. That is queue. So BFS follow queue. First in, first out. This is the application of data structure. You know, data structures are used everywhere. Whenever you implement an algorithm, we have to use some kind of data structure. Here, because it is first in, first out, C1 is considered first. So what happens to C1? C1 is explored. First, C1 is checked whether it is a goal node. Is C1 goal node? No. Because C1 is not a goal node, it is removed from the open and placed in the closed and bring what to bring? C1 successors, which are C11. Oh, successors means in queue, addition is at the rear end, right? In queue is like this. This is front, and this is rear. So apparently, whenever you add new elements, you add at this side. Whenever you remove element, you remove from this side. Therefore, here, I need some more space. This is gone. So C11, here C11 and C12 is added, inserted in this queue. Do you understand, students, all this, whatever I'm saying, or do you have any doubt?
Clear, ma'am.
Clear?
Yes, ma'am.
Very good. Anything you don't understand, you please ask. These are very important things. These are useful for your for interview questions also. In interview questions also, they ask BFS uses queue or stack. So here C11, C12 is added. Next, which element is to be considered from this queue? Yeah, anyone student, please?
C2, ma'am.
C2. Why C2? Because it is at the front. And you see, are we following depth first strategy here? Yes, because we have to go to C1 first, then to C2. The depth first strategy is correctly implemented. C2 remove from first check. All right. First check whether C2 is goal. C2 is not goal. If it is goal, the search procedure stops. It does not proceed further. C2 is not the goal. Therefore, C2 is moved from open to closed, and here whatever are C2 successors added in at the rear of the queue, open queue. All right, students, let me show you. You all have to complete this, please. If you don't understand, you can ask anytime. Let me show you the algorithm from the book so that you get the idea. Actually, uh, I showed you the implementation details. The algorithm would be this one. We are here, exhaustive search BFS. Read this algorithm. Algorithms are very important. When you become developer in software, you will be given in this format the requirement. You have to write the code for this requirement. This is like an algorithm. If an algorithm is given, you should be able to understand it and code it in programming, any programming, whichever you know. So this algorithm has input start and goal nodes. There are local variables open, closed, state X, successors found. The output is yes or no. If goal is found, it replies yes, otherwise it replies no. The method is initialize open list with start and closed is equal to 5. Means there is nothing in closed. In open list, there is a start. Or found equal to false. Okay, we have to, students, today I'll give you one activity. You write the code in Python for this BFS. Okay, only for BFS. Although we will study now DFS and all, but try to write the code for DFS by just looking at this algorithm. Found is a variable that is false, while open is not equal to 5. Means if there are some elements in open, until that it executes. And found equal to false. If found is true, while will not continue. All right. If open is nil, even then while this loop will not continue. So what is the condition here? Open should have an element and found it should be false. Only then it executes this while loop. In this while loop, it removes the first state from the open and call it state X. Whatever I did know there, that choose one state from the list and call it state X. Put state X in the front of closed list. Okay, keep it in the closed list. Closed list is maintained as a stack. And if state X is a goal, compare, or this is comparing or checking whether state X is goal. If it is goal, then found is true, and why there is a the procedure would stop. If goal node is not found, if it is not goal, if condition would return false. If when it returns false, uh, here this has to be executed. What is this? Perform expand operation on state X. We are expanding. How are we expanding? Uh, by inserting or loading or adding its successor in the open list. Expand operation on state X producing a list of successor. Remove successor from those states, if any, that are in the closed list. Okay, if there is any successor that has been uh, added in the closed list already, means already it is explored, then we have to remove it. We should not have it in open list. This point states that append successor at the end of the open list. Because open list is a queue, we have to append it at the end, means at rear end we have to add. And while if found equal to true, then return yes, otherwise return no. All of you understood this algorithm? Yes or no? No means I'll explain again. Respond in the chat window.
Please explain to me.
Again, once again.
Yes, ma'am.
Okay. This is a BFS algorithm. In this algorithm, we require start state and goal state. We should specify Like yesterday, I showed you one program. The program for this, um, what is a problem? In this program, we have specified the capacity for first jug, second jug. We have specified the initial states of both, and we have specified the final state, goal state. These have to be specified when we are writing program. That algorithm states the same thing. It says that it requires an input and start and goal state as the input, and it requires local variables, open, closed, static. These are the variables that are required. Here in this program, what are the variables that are required? A and B. Only two variables are required because there are two jugs. Here we require more: open, closed, static, successor, and found. Where open and closed are list variables, means open is a queue and closed is a star. Statex is just a single value. Successors is a list again. It might be single or multiple. Found is just a Boolean variable. All right, you have to declare like local variables. And what would be the output of algorithm? It could be yes or no. When it is yes, if it finds the goal node. No, if it does not find the goal node. And what is the method? What is the method to find the goal node? Initially, open list has to be assigned with a value start node. In open list, you place the start node, and close list is 0. Okay, there is nothing in close list. Found, which is a Boolean variable, is initialized to a value false, because found will keep track of whether the goal node is found or not. So initially it has not found, so it is false. Now while loop begins, this is loop because you have to go on expanding the nodes in a breadth-wise manner until the goal node is found or all the nodes have been explored. There are two options. Either you find a goal node or there are no nodes to explore further. In that case, there is no goal node. That's what is checked here. If there are no nodes, if there are nodes, and if it is not found goal node, this procedure is executed. Otherwise, it is not executed. There is no use, no, there is no actually meaning in performing this activity if there are no nodes. And then how it performs, whatever I explained you here. First start with goal node. First it starts with the start node. Take the start node, put in the open list. Same thing here. Remove the first state from the open and call it state X, because in open list we have placed start. So we are removing start from here. Same thing. Take S. Check whether it is goal node. If it is not goal node, place it in closed. Remove from open and keep it in closed. And at the same time, essentially you have to bring the successors of S. What are the successors of S? C1, C2, C3. So C1, C2, C3 are appended to the open list because it is a queue. C1, C2, C3 are added. Same thing it is saying in the algorithm. What it is saying, remove the first state, call it state X, just giving a name. To S, it is giving state X is equals to S. Now, is state S, yeah, if it is first putting and then checking. All right. What I explained you is first checking and putting. But here algorithm is the other way. There are multiple ways of doing the things. All right. So first it is putting in close list. There is a close list. It is actually a stack. So it puts S in the close list, and then it compares whether S is goal. Because S is not goal, it performs these three functions. What are these three functions? Expand S. What are the successors of S? Here we find there are three successors of S. Expanding it, bringing those successors in the open list so that we can explore them. And then remove any successors if it is already available in closed. Suppose if something is there in the closed list, uh, C12 from C1 as well as from C2, if there is a path like this, and suppose if it is already been explored in under C1, it should not be explored again for under C2. If it is available in closed, that should be removed. That is one point. And last point is append all the successors at the end of the open list. This procedure continues until a goal is found or there are no nodes. And then it exits. Apparently, it checks whether found is true or not. If it is true, it returns yes, otherwise no. All right, students, because these are very important topics, it will be useful for you throughout your career. That's why I am emphasizing and explaining again and again. Even if you don't understand, you can ask. This will be very useful for you. All right, students. So this is about BFS. That is the first strategy to, okay, comparison we'll do later. First strategy to perform exhaustive search. Second strategy is DFS. 1 minute, students. In DFS, which stands for depth first search, the search procedure goes down in the first path until it finds the leaf node, and then it back up, go down in that direction, and again back up and goes in that direction until there are no more leaf nodes for that particular node. The same we will use, or I should do again this one. Okay, I'll do again. Start S. In DFS, you start with S. Consider its first child, and then the first child of the first child, then its child, here because it is dead end, here there is nothing further to expand, to explore. What it does, it go up to its parent and see whether it has any child, because this has to complete exploration. Only then it moves to its parent. This is how it performs. Here, suppose there is C112, then the search would take to the C112. It is like this is 1, 2, 3, 4. All right, and then it comes here. It goes to its parent. Here, parent. At parent, suppose there are two more successors, C112, C13, C1, C11, C12. There is no need of two ones, C12, C13. And then here, what happens is this when it goes to C1, again it checks whether it has any other successes. It has, so it explore that, and then it goes back to C and come to not 3, 5. It should be 5, and this should be 6. And this left side is completed totally, S now would start from the second child. Again, second child should come down to the leaf part and again go up. While coming up, it has to explore the remaining successors. This is depth first search. It is going in vertical direction. All right. So let us look at the example. Here, search tree for what is a problem. In the beginning, it is start state is 0, 0, and then it has two. Actually, it has 5, 0 and 3, 0. But it takes the first root 5, 0. Again, 5, 0 would have several alternatives. 3, 0 will not be explored. It is going in this direction, in one direction. After 5, 0, it will take 5, 3, then 3, 0, 3, 3. It is last in, first out. Here there are several other, no, not this side. It would be this side. This side. It would have some more successes, but it has to travel in this direction only until it finds the leaf node, last end. Then it start exploring. So 3, 3, 3, 5, 1, then 0, 1, then 1, 0, and 1, 3, 4, 0. This one way. All right. Suppose if it is available. Suppose if the goal is available in this route, it would be found. Otherwise, it would not be found. It would lead to unsuccessful search, and then it comes back to one by one to their respective parent nodes, and in this manner the procedure continues. Do you understand DFS, students? And do you understand BFS? No response means you are not understanding.
Yes, ma'am, understood.
Very good. Now let us see its implementation. Like BFS, it also has open closed. Anyone please tell me how to implement open? Okay, let us see how it works. Then you tell how to implement open. What is the data structure to be used? S. It begins with S, the start state. Then from S, what it has to do simultaneously, let us check the algorithm. It has got a start, goal, states of the problem. It has variables open, closed, record X, successors found. What is the difference between this output and the previous BFS output? Read and tell me. Shall I open that also? You read this. Okay. Please read this output of DFS. Now let me show you the output of BFS. Here, this one. Please tell the difference. Anyone? Students? What is the difference between the output of BFS and DFS? No? All right. The difference between the output of DFS and BFS is when in BFS it just print yes or no, whether the goal node is available or not available. In this program, what is a problem? If goal node is available, it prints yes or no. But this here, it is printing the complete steps, sequence. It is printing the sequence. Here in this example, BFS, it is not printing the sequence, just printing the yes or no Boolean value. Whereas this DFS is printing the path sequence from where to where to where, which node to which node. That sequence has been printed in DFS. For that purpose, it requires an extra variable. Method is to initialize open list with start and nil. Why start and nil? Because here we are keeping track of the path. From start, where are we going? From the successor, where are we going? So initially set is empty, found is false, while open is empty. Open is not equal to nil, means open has some elements, and found is false. Do same here. Remove the first record, start and nil from open list, and call it record X. Put record X in the front of the closed list, which is maintained as a stack. If state X of record X is equals to goal, then found equal to true. Otherwise, expand state X producing a list of records called successors. Create each record by associating parent link with its state. If you associate parent link with the states, with the successor states, essentially we can trace the path. If we don't associate parent and its successor, we can't trace the path. Remove from successor any record that is already in the closed list. Insert successors in the front of the open list. And here it is mentioned open list is stack. If found equal to true, then return the path. Here we have to return the path. In the earlier example, in the earlier algorithm, it was returning yes or no. That's it. Here it is essentially returning the path, complete path, because it has traced it on the closed list, else return no and stop the procedure. So how it is done? It starts with first start node S, and then start node is, here it is nil because start node has no parent. This is now moved to closed S dot nil and removed from here. While removing, because open is a stack, we will create a stack. In the stack, it places All right. Here, it places. If we start from placing from left to right direction, then C1 and C2 would come, and C2 would be on the top. C2 would be explored. Let us do from this side, right side. So C2 and C1 are added into the stack along with the parent details. What are the parent details? C2 and C1 from where you have uh, approached. You have approached C2 comma S. This is C1 comma S. From S we got to C1 and C2. This is our stack. Next, in the next iteration, open is checked. Does open has element? Yes, open has element. Next, well here C1 comma S is chosen. It is popped from the stack, popped out and placed in the popped out placed in C1 comma S. So it is not there in open. When we are popping it out, when we are removing it, exploring and removing it from this open stack or open list, we are also adding its successors, because in the algorithm it is mentioned. Put record X. What is record X now? C1 comma X S S. C1 comma S is in record. It is put in the front end of the close list, and it is checked whether it is goal. It is not goal, so we have to expand it. How to expand this? Again, I am following right to left approach. This is also stack, so C1 should be added in the top. This is S comma nil, then C1 comma S. Now in this stack, we add C2 comma S will remain as it is. Next, C13 comma C1, C13 comma no, C12 comma C1, C11 comma C1. Now these are added, not appended, added into the open list. All right. Next, what happens? Choose the top element in the stack to explore. So I am choosing C11 comma C1. This element. This element is moved to the close list here on the top, C11 comma C1, and removed from here. What does it demonstrate? It demonstrates that we are going from S to C1 to C11 to C111 in this direction because of stack. All right, students, this is how DFS operates. Next, let us compare DFS and BFS. It is given here. I'll write down the points and compare, and then move on to the next topic. Not topic, move on to the next strategy. The comparison. BFS, DFS. Anyone can say any points regarding this? Do you find any difference between DFS and BFS? Not finding any difference?
BFS is
BFS for
horizontal one, whereas DFS is vertical.
So this is breadth-wise. Because it is breadth-wise, which is data structure it uses?
Q.
Q.
So it
Q.
uses queue. It is queue-based and it is stack-based. What about efficiency? Which one you think is more efficient? Okay, in terms of memory, which one requires more memory?
DFS.
DFS require more memory. Why?
It has to check ev-
Let me clarify this. BFS requires more memory because it is exploring in the breadth-wise manner, and if there are many nodes, if there is an exponential growth, it requires more memory. It requires relatively less memory because it is going only in one direction. It is not expanding everything. BFS expands everything, and BFS is superior if goal is, where is the goal? Here, let us check. Uh, BFS is doing in this manner, breadth-wise manner. Consider that our goal is here. Then which method or which strategy would find the goal first? If the tree is in this manner, then which strategy would find the goal first? BFS will find the goal first. Why? Because BFS would expand level 1, then expand level 2, then expand level 3, and at level 3, goal is found. This is BFS. What DFS does is it expands all the children in this direction until it finds the last leaf node. Further, it completes this part totally. It finishes this part totally, then move on to this one. You see here, there are more nodes to explore at this side. Students, it varies. This is one example. If here, if this side there are no nodes, there is a possibility that DFS would find earlier. However, the exploration of the nodes in one path until the leaf node would sometimes not give efficient results. Suppose if our goal node is this, And here also there are two cases. If our goal node is here, then DFS would find earlier, because BFS have to finish third level, fourth level, and fifth level. But it only after exploring 1, 2, 3, 4, 5, 5 nodes, DFS would find the goal. It depends where is the goal, and it depends how many nodes are there. There are several factors. Whatever I am discussing here is not fixed. It is about the variability that exists, the dynamism that exists in mm, different strategies. BFS is superior only if goal node is found at the upper portion, at the upper section. All right. If it is at the upper section of the tree, then BFS is superior. Here, this DFS is superior when goal node is in one in the starting path. When it starts and in the starting path only if goal node found, then it is. But overall, BFS is optimal. BFS is optimal because it searches level wise. DFS is effective when there are only few subtrees and connection. There are few connections, and there are this effective if few subtrees. DFS is best when goal node exists in the lower left portion here. Okay, here I will change this to lower left portion. Here it is upper portion. And DFS is memory efficient if the path from the start to current node is stored. Okay, in this way it is efficient, because if it is storing the path, it would later retrieve, and each node should contain the state and its parent. DFS may not give optimal solution. This is not optimal. Finally, the conclusion is DFS is not optimal, not. And the conclusion is BFS is optimal in general and average scenario, in general case. And when the people have studied many algorithms, many trees, and executed these algorithms, they found that on average DFS is not optimal, BFS is optimal. In some cases DFS might be optimal, but BFS is optimal in more cases. All right, so what did we understand? We understood that there are some advantages of BFS, there are some advantages of BFS. So the next strategy, the next method, the third method combines both the features of DFS and BFS, which is known as depth first iterative deepening, DFID. Depth first iterative deepening, this combines advantages of DFS and BFS. BFS is memory efficient, BFS is not. BFS is optimal, DFS is not. Therefore, we can combine both the features, memory efficiency and optimality, into DFID. How DFID works? It starts with initial state. It works level wise again. It starts with initial state, Is initial state the goal? This is initial state. No, it is not the goal. Then in the first iteration, uh, it generates the successors of start, all the successors of start, and checks whether both are whether any one is goal. If no node is goal, it goes to second iteration. What does it do is it expands this left child and check whether any one of the successors of the first child is a goal. If they are not goal, then this moves to parent, and here it is already generated. When it has gone here, parent, it generates the second child and checks whether this one is goal node. Consider that this has only one. If not, it goes to third iteration. Will anyone tell me how it is expanding? It is not totally breadth-wise and not totally depth-wise. It is combination of both. Initially, it expands both the successors, so it is breadth-wise. In the second iteration, it goes to depth-wise, and again breadth-wise is combined here. It goes to left child, again left and right, and then moves to the parent. Again, parent would expand. This part is DFS. This part is BFS. Both are combined in the same iteration. In the third iteration, it checks whether there is a goal node in the left path of the uh, tree, and this is going in depth-wise. Depth-wise, it goes to its parent. From here, it goes to its parent, and here, this is what it does is here it expands the parent, this parent. It expands this. It is like this. And then it goes back to from here. No, this also has its subchild, sub node. This way, it is again depth first. Okay, both the nodes have been explored. There is no goal node. Then from here, it goes to the start node, which is the root. Again, what it does, this is already done. Okay, this will be there because it is already expanded. This is expanded. Now what it does, it try to expand its another child, and then from here its successor and successor. Please observe, it is not totally depth and not breadth. It is combining both. It is checking whether it is there. Further, it is not going down. Suppose if further there are nodes, it won't go down because in third iteration it finishes third cycle by following depth and breadth. Is it clear, students? Depth first. This is input, start and goal, local variable found, output yes or no method initialize d equal to 1, depth of the search tree while found equal to false do perform the depth first search from start to depth d. So depth wise it is doing means first d1, d equal to 1, d equal to 2. If goal node is obtained then found equal to true, else discard the node generated in the search of the depth d and increase the depth. If it is found, it returns yes. All right. The last strategy under exhaustive search is bidirectional search. Bidirectional search. In bidirectional search, search proceeds from start as well as from the goal. In both the directions, search starts. And there would be a meeting point whenever both the search pointers meet, and then it starts the search. It stops the search procedure because the path has been found from start to goal. Let us discuss this. So this also works in iteration. When k equal to 0, it is a start, and there is a okay. They are using this tree. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13, 8 and 9, 2, 7, 12. Then 11, 14. This is 16 and this is the goal node. 12, 15, 13 also 15, and from 15 this is the goal node. This is our search tree. How bidirectional search proceeds? Let us look at that. We start with 1. We are going in the forward direction. When k is equals to 1, from 1 we have okay when if k equal to 1 and k equal to 0. K equal to 0 means from goal. From goal it is here 16, and k equal to 1 from start it is, this is backward direction. From 16 we have 14 and 15. Later k is 1. This is goal. From goal. From goal. This is from start. Start 1. From 1 we have, this is forward direction. From 1 we have 2, 3, 4. Then k1 is over. Then k equal to 2. K equal to 2 is for goal. From goal, we have k equal to, what we got from k equal to 1? 16, 14 and 15. This is k equal to 1. Then 2, k equal to 2 means 11. From 15 we have 12 and 13. This is backward direction, goal from goal. Then you please compare what I'm doing here with this. But it is going up now. Here, start. A equal to 2 for start. 1, 2, 3, 4. Here 5, 6, 7, 8, 9. This is from in forward direction. Then k equal to 3, k equal to 2, k equal to 1 in goal, from goal state. It is 16, 14, 11, and here 6. This is from back. It got connected. Therefore, here what happens is a path is established. 1, 2, 6, 11, 14, 16. This is bidirectional search. Okay, how to perform analysis? How to perform analysis of I want to complete. Okay, first analysis. Analysis means how to evaluate the algorithms and compare which one is better. With respect to time, space, and solution, search techniques DFS, BFS, DFID, and BDS. With respect to time, BFS is O B to the power of D, big O, and DF is O to the power of BD. This is OB to the power of D minus 2. Time, space. Students, tell me which one is better out of these four with respect to time complexity. OD, OBD,
BDF.
BDS is better. Very good. Why? Because it has D by 2. Depth, B is breadth, D is depth. So depth by 2 means half. Therefore, with respect to time, BDS is efficient. With respect to space, which one is efficient? You tell me. O of BD by 2. With respect to space, which one is efficient? This is OD, means depth. If depth, there are 8 nodes in the depth, only 8. If suppose goal is found. And BFS is OBD, B to the power of D, breadth to the power of D. If breadth is 5 and depth of each is 4, it will be 5 to the power of 4. And this would be, suppose if goal node is found uh, in the left section, then this would be just 8. This would be 5 to the power of 4 requirement, memory requirement, because we have to store the nodes. This is OD, just the depth, DFID. And BDS is B to the power of D minus 2. So from this we understand that DFS and DFID. Just this is just D, but this is power. Whenever you get power, it will be more. If you have just a value, it would be linear. You have linear, exponential, uh, time complexities. If it is just OD, it is efficient compared to OBD. And with respect to solution, BFS is optimal and DFS is optimal. What do you understand from this? DFS is combining the space efficiency as well as BFS optimality, both DFID is combining. So DFID is both optimal and space efficient. From this, we conclude that DFID is the most efficient technique when you compare to all the four exhaustive search strategies. All right, this is about analysis. Next, will anyone tell me traveling salesman problem? What is it? Does anyone know traveling salesman problem? No one knows traveling salesman problem. Suppose you consider Zomato or Swiggy or any delivery boy or delivery agent. What is their task? Their task is to deliver the products. What is their goal? What will be their goal? Anyone please tell
Delivery
me what is
item.
their, yeah, to deliver the item?
By using the shortest path and connecting all the nodes. I mean, all
Exact,
the delivery addresses.
exactly. This is the perfect answer. It has to follow the why it has to follow the shortest route. Tell me the reason.
To save the fuel charges and distance, I mean, the kilometers traveled and energy also.
Time also. Very nice. So, if you know, if this delivery boy knows the shortest route from one place to another place, from source to destination, there will be several paths, several routes, and this will be connecting. There are four routes. One, two, three, four. There are four routes from source to destination, and also he might have uh, more than one order, two, three orders. He has to connect. He has to, and even Ola and Uber also. You see, they have to find the shortest route. If they find the shortest route, then as Pawan said, fuel fuel will be saved. It means that our amount will be saved. So it gives monetary benefit. It gives time benefit. It gives mm, it makes the delivery boy more efficient. So he may get good reviews. So very good feedback he can achieve. There are so many advantages if he knows the shortest route. That is traveling salesman problem. If a salesman is traveling, look students, if one person is going from one area to another area, that would have perhaps two, three connections. Just to go from Nizam College to Osmania University, yeah, how many routes are there? So many routes are there. And if suppose a salesman is traveling cities of our country, okay, he wants to travel all the cities, Hyderabad, Bangalore, Chennai, Kolkata, Delhi, everywhere, every city. He there he want to go to Punjab and Jammu and Kashmir, Kerala, everywhere he want to go. By following the shortest path. Do you think it is possible? Do you think he can find the shortest path? Perfect shortest path means it should not be uh, greater than any other path. It should be the least path. Is it possible?
Yes, ma'am, possible.
Pawan,
Possible, ma'am.
how is it possible, Pawan? We'll see here. If there are n cities, And if he has to travel uh, from source to destination back to source, because see, this Zomato person, he has, suppose if he is taking from a Bahar restaurant, he go to that place, delivery place, he come back to Bahar only. Okay, so he has to travel from source to destination and back. It's to and from. So it requires n minus 1 factorial. If n is 2, 3, it's fine. 2 factorial, 3 factorial, 5 factorial is also fine. If suppose if it is 15 factorial, what will be the value of 15 factorial? This this is known as very difficult and toughest problem yet to be solved. It is not totally solved. This problem is being researched by scientists and researchers across the world, but they are not able to find the right solution in see finding right solution for 1 year or 2 years, that is not the right solution. They should find the solution in short time. They might find, perhaps it takes 10 years or 15 years, but that's not the optimal solution. They should find the solution within 1 hour or 2 hours or 10 minutes. It is a combinatorial explosion. If n cities have to be examined, if number of cities grow, the time required to wait for Salesman to get the information about the shortest path is not a practical situation, because how many, there may be several routes. If any short, it's okay. If there are only 3 routes or 5 routes, but it's not the case. If you consider 10 cities, how many paths will be there in that? It's not possible. It's not a practical. It is a combinatorial explosion problem. So, but then there are some solutions. They are known as suboptimal solutions. Suboptimal means it is not perfect, it is not optimal, but it is near to optimal, near to perfect. So start generating complete paths, keeping track of the shortest path found so far. Stop exploring any path as soon as its partial length becomes greater than the shortest path length found so far. This is one strategy. In this strategy, C1 is the start city, and there are distances or the cost. The cost is mentioned. This is the graph for traveling salesman problem. If he go from C1 to C2, and he has to explore all the cities. It's not like a Zomato person has to go to one house, 2 house, or three places. But here, in this problem, he has to explore every city. So C1 to C2, if he goes, it is 7. C1 to C3, if he goes, 11. The cost. So in the solution, it begins with C1, go to C2, means cost is 7. C3, C4, C5, again back to C1. So 7, 20, 13, 5, 15. The current path is 60. Means we should start with some path. So C1, C2, C3, C1, C2, C3, C4, C5, C1. So C1, C2, C3, C2 to C3, C3 to C5, C4, C4 to C5, C5 to C1. Okay, this is the first initial path, and its distance is 60. The distance or cost, it's a metric. It's 60. This is the current best. I explore another path, C1 to C2, C3, C5, C4, C1. C3 to C5 also there is a route. C1 to C2 to C3 to C5 to C4 to C1. In this path, the distance is 61. So we should not consider. We should just stop this. Don't X. And then third path. Like this, there are several paths. No. All the paths have to be explored. This is 72. And one path C1, C2, C4, C5, C3, C1 is 50. So 50 is less than 60. Current best is 60. 50 is less than 60. Therefore, 50 is chosen to be the current best path. Like this, they explore all the possibilities, and then They found 48 C1 to C2, C5, C4, C3, C1. And one more path gives 48. So 48 is the shortest path. Like this, we have to continue for every combination. All right. This is one solution, but this problem is discussed at this point in time here to tell you that exploring all the paths is not efficient. It's, sometimes it is not possible, sometimes it is inefficient, sometimes uh, you get exhausted. That's why these techniques are known as exhaustive searches. In exhaustive searches, we are trying every possible combination. Suppose if I am new to a city, I don't know anything, I have to perform exhaustive search. Exhaustive search has got lot of disadvantages. That's why we have to move to heuristic search, get the information about the domain, and then find the solution. That solution would be uh, more efficient compared to exhaustive. Exhaustive is all about exploring everything that is available. Everything that is available that is not efficient. Understand, students? That so tomorrow, not tomorrow, next class, we will start our the next topic, which is exhaustive search. How, sorry, heuristic search. Exhaustive have been completed. Next, we would begin heuristic search and see how heuristic search is better, efficient compared to exhaustive search. All right, students. Today you have to write uh, 10 to 10:30. We have awareness program on ICC, so all the first year students need to join. You should have uh, unmuted and told me no. Okay then. Anyway, I'm ending. I'll post the question. Now you join. At least something you will get. If there is something important, students, you can unmute and you can inform me. Sometimes